Paper 2 from May 23, Timezone 2. Starting off with analytical techniques to work out the unknown organic compound X. We're given the percentage abundances of carbon and oxygen, with which we can deduce the percentage abundance of hydrogen, the missing constituent element. To work out the empirical formula, always draw the table that consists of three columns corresponding to the constituent elements carbon, hydrogen, and oxygen. I'm going to put hydrogen at the middle because usually the empirical formula for hydrocarbons start off with carbons and then hydrogens. I will draw three columns and I'll introduce the first row, which is going to be the percentage abundance. Carbon 48.6, hydrogen, if we do the math, 100 take away 48.6, take away 43.2, it would be 8.2, 43.2. Second row, we will introduce the relative atomic mass. For carbon, 12.01, hydrogen, 1.01, oxygen, 6.0. We will divide percentage abundance, assuming that's the grams, the mass in grams for 100 grams of the sample, divided by RAM to give us the amount in mole. Do the math, we'll be given 4.05, 8.02, sorry, 8.2 and 2.7. To work out the ratio of carbon to hydrogen to oxygen, we will divide by the smallest amount value, 2.7, to give us 1.5, 3 roughly, and 1. For empirical formula, we need the smallest whole number ratio, for which I'm going to convert the 1.5 to 3, hydrogen to 6, oxygen to 2, so that we end up with carbon 3, hydrogen 6, oxygen 2 as our empirical formula. The second question, unfortunately, does not have the mass spec data. But if we did, we were probably going to be asked what the fragments correspond to within the unknown compound X. We always know that the higher or the highest mass to charge ratio value will correspond to the molecular ion peak. And we can assume that the highest mass to charge ratio would be 74, for which the diagram, the mass spec data, would look something along the line of y-axis percentage abundances, x-axis mass to charge ratio, where there would be small peaks, small fragments there and there, but there will be the large significant peak at 74. There will be another large significant peak at 45. 74 will always be the highest mass to charge value, will always be the molecular ion peak. And 45, we will actually have to refer to section 28 to figure this out. Let's have a look. Data booklet, section 28, tells us that a fragment with 45 mass corresponds to a carboxylic group, COOH. Therefore, we will write COOH here. What does that mean? That means a fragment, there should be another fragment that corresponds to the mass 29. There should be another fragment with mass 29, and we can assume that to be either an ethyl group or an aldehyde group. Probably an ethyl group, so that we have an ethyl fragment and a carboxylic group fragment, which makes a propanoic acid. And propanoic acid is going to be C3H5COOH, which if we turn into molecular formula should be I said 3 C3, it should be C2. C3H6O2, which aligns well with our empirical formula. We know the molecular mass of X is going to be a multiple of the empirical formula mass. And what's the empirical formula mass? C3H6O2 in total leads to 12 times 3 plus 1 times 6 and 16 times 2. Now that's 74. So the empirical formula equals to the molecular formula. Therefore, our molecular formula is going to be C3H6O2. Infrared spectrum of X is shown where we have two peaks, one at 1700 to 1750. Now we know that to be a carbonyl. Now we have another broad peak between 2500 to somewhere between 3200. Now what does that correspond to? It corresponds to a hydroxyl group. There are two hydroxyl groups, one in an alcohol and one in carboxylic acid. We know that for our purpose, it would make sense to have an alcohol in carboxylic group as we are looking at a propanoic acid. Therefore, A should be hydroxyl in carboxylic acid. B, a carbonyl in carboxylic acid. The next question is about equilibrium, where we're going to start off by interpreting the Kc value of 0.0665. Now, what's the significance of Kc value? Kc value can be either bigger or smaller than 1. If bigger than 1, it means that the position of equilibrium lies to the product side. If less than 1, that's less than 1 and bigger than 0, the position of equilibrium lies to the reactant side. And that's what we're looking at. We can tell that the position of equilibrium lies to the reactant, which means that the reaction does not proceed forward. The reaction hardly proceeds. Reaction hardly proceeds is what we can interpret. N2O4, dinitrogen oxide, turning into nitrogen dioxide, is the reverse reaction, which means that the Kc4, the reverse reaction, is the reverse of the Kc for the forward reaction. Let me repeat this. Kc for the forward, the original is N2O4, the product concentration over reactant concentration. But the Kc for the backward is what? Kc backward is in fact NO2 over N2O4 concentration. So how do we work out Kc backward? Well, if I do Kc forward, 1 over Kc forward, that will give us Kc backward. Which means what we'll do is 1 over 0.0665, which is what? Which is 15. Do the math, it's 15.0. Enthalpy change can also be calculated, delta H, for production of nitrogen dioxide if we are given delta H F values. Delta H will equal to the delta H F product minus delta H F reactant, which means that the product delta H formation value is 33.18. But let's make sure that we multiply this by the molar ratio 2. Take away 9.16, which will give us, if we do the math, 57.2 unit kilojoules per mole, the same as delta HF. Dinitrogen oxide will have a formula along the line of single covalent bonded nitrogen and nitrogen that are each double bonded to one oxygen, and single covalent bonded to negative oxygens. This is because the central nitrogens are positively charged. Let's draw the lone pairs. 2 lone pairs for the double bonded oxygens and 3 lone pairs for the single covalent bonded oxygens. Lewis structure of N2O4, double bonds between oxygens and nitrogen, double bonded oxygens and nitrogens, and negative oxygens and nitrogen singles. NO bond lengths are all equal, and the equal bond length suggests that we have resonance structure, as we would expect. We would expect there to be resonance structure along the line of this. Resonance, presence of resonance. Predict ONN bond angle, where we would expect, well, we would expect this to be 120 degrees, trigonoplanar, 120 degrees. Nitrogen oxides, NO2, dissolve in water and will produce 2 acids. Okay? NO2 dissolve in water to produce, if it wants to produce 2 acids, it will need to start off with 2 nitrogen dioxides to produce HNO3 and HNO2. One we're familiar with, we use a lot, which is nitric acid. That's the strong acid. What about the second? HNO2 produced is the nitrous acid. That's weak acid. We have an electrolytic cell of molten magnesium chloride, where we have on the anode chloride ions being attracted and being oxidized. In the cathode, magnesium 2+ ions being attracted to be reduced. Product formed at the cathode will be magnesium solid. That will be physically observed as a layer of magnesium metals being deposited. Electrons will be migrating from the anode to the cathode. Graphite. Graphites are giant covalent macromolecules where there are layers of carbons, layers of carbon atoms that are joined together by LDFs, and each carbon within the layer has a delocalized electron, and it's the movement of these delocalized electrons that leads to electrical conductivity. Layers of carbon atoms in giant covalent network where each carbon has delocalized electrons, and it's the movement of these delocalized electrons across the carbon layers, electrical conductivity. We can use Winkler method to measure the amount of oxygen present. Let's do some recap on how we can use the amount of sodium thiosulfate solution to deduce the amount of oxygen present. Well, firstly, 1 oxygen is going to produce 2 manganese oxide, which means that 2 manganese oxide will produce 2 iodine, where 2 iodine will react with 2 iodides to produce 2I3 minus, where 2I3 minus will react with 4 thiosulfate ions. So 1 mole of oxygen ends up reacting with 4 moles of thiosulfate ions, which can be summarized as the amount of oxygen equaling to the amount of thiosulfate over 4. Yes, that's right. 4 thiosulfate will equal to 1 oxygen. Therefore, we can do the calculation as follows. We know the concentration and the volume of sodium thiosulfate, meaning we will 0.036 multiply 0.005 over 4 to work out the amount of oxygen, but we're not interested in the amount of oxygen, but concentration, for which we will further need to divide the amount of oxygen by volume of water in which oxygen is dissolved in. Now that volume is how much? 150 or 0.15 dm cube. Therefore, let's further divide our amount value by the volume, 0.15 dm cube, which tells us that the concentration of oxygen is going to be 3 times 10 to minus 4 mole per dm cube. Now we use the Winkler method to derive the oxygen amount, the concentration of oxygen. But to actually work out the biochemical oxygen demand, what we do is we apply a known amount of oxygen to a sample of water. We leave 5 days, during which the aquatic life within that sample of water will have respired and consumed oxygen, so that the amount of oxygen available in that sample will have decreased. And that's what we measure. The measure oxygen amount in day 1 and 5, where the difference between day 1 and 5 equals to the biochemical oxygen demand, which may be high or low. If it's high, it means that the difference between day 1 and 5 is large, meaning that a lot of aquatic life has been respiring a lot, consuming lots of oxygen. If it's low, in our case, low BOD value would indicate that we have low oxygen consumption, due to low population or low amount of aquatic life. Bismuth is an element with a huge atomic number, 83. Now, to derive the electronic configuration would be a lot of work, but if we identify bismuth on the periodic table, we can see how it's on period 6, group 15. Electronic configuration would be condensed with Xe, xenon, 6s2. Let's write that down here. Xenon, 6s2, 5d10, 6p3. Why? Because we are in group 15. 6s2, 5d10, and then 3p, 6p3. We're not supposed to know, we're not supposed to give this electronic configuration, but deduce two pieces of information. What key information can we deduce from this electronic configuration? Well, first, we've got 6 electron shells. We've got 6 energy levels because we're on period 6. Period 6 tells us 6 energy levels are present. Group 15 tells us that we have 5 valence electrons. These are the two pieces of information we can deduce, but we can go further. What else can we say? Well, 6p orbital has 3 6p orbitals that are identical in energy level. 3 electrons will fill the 3 orbitals as single electron in each orbital with parallel spins, which means the 3 electrons in the 6p orbitals will be unpaired. Unpaired 6p orbitals, electrons. You may choose to indicate 6p or not, does not matter. Malleability is a common physical property of metals, and that is because metallic bonding allows lattice of metal cations to have multiple layers that can slide over each other when force is applied. And likewise, aluminium ions exist in lattice of layers where layers of Al 3+ ions can slide over each other when force is applied. Calorimetry, Q equals mc delta T, where mass is 11.98 grams, specific heat capacity, not water, but aluminium with 0.9 or 2 joules per gram per Kelvin. Finally, the temperature change. Increase from 18 to 40 degrees Celsius, meaning that we're talking about exothermic reaction, and 22 degrees Celsius or 22 Kelvin. Let's do the math with units cancelled out, grams, Kelvin, so that our value will be in joules. 238 joules. Are we specifically asked to calculate the answer in a particular unit? Joules or kilojoules? Joules. So we leave 238 as it is. Argon has 3 isotopes. Therefore, 3 different masses, 36, 38, 40. Technique to determine the relative abundances of these 3 isotopes is mass spectrometry. Once we are given the specific percentage abundances of each isotope, we can multiply the percentage abundance, 0.34, multiplied by 36, the mass number, have them added to the other isotopes. Now, from the look of how the major percentage abundance is for the largest mass isotope 40, we know that the value, the relative atomic mass value will be close to 40. If we do the math, the value would be specifically 39.99. Cobalt is where? Cobalt is in d orbital, the first row of d orbital after iron. So that is the seventh, it's the seventh 3D element. We want the full electronic configuration, so we want to write all the way until argon. 1s2, 2s2, 2p6, 3s2, 3p6, and then from here 4s2, 3d7, the seventh 3D element, transition metal. Because we're dealing with a 2+ ion, we want to remove 2 4s electrons. Why? Because occupied 4s electrons, occupied 4s orbital is at higher energy than 3D. Titration question, where we have the analyte, methanoic acid, being titrated with the titrant, sodium hydroxide. We have unknown concentration of our analyte methanoic acid, and we're trying to find that concentration. We're not given the volume of sodium hydroxide added to neutralize the analyte, but if we do, we can work out the concentration of methanoic acid. We'll start off with working out the pH of our titrant sodium hydroxide, for which the information we need is the initial concentration of sodium hydroxide. Why is that? It's because to work out the pH, we need either the OH minus concentration or H plus concentration. In our case of strong base sodium hydroxide, we need the OH minus concentration, which would equal to the concentration of NaOH, because being a strong base, NaOH completely dissociates into Na plus, NOH minus. Therefore, OH minus concentration we know, meaning we can work out the POH. POH would be minus log and then 0.2. If we do the math, this will give us 0.699, which is quite a high value. And knowing the POH value, we can work out the pH value by taking away the POH from 14. And where's that? pH equals 14 minus POH equation from ionic constant of water. Therefore, pH would equal to 13.301. HCOOH aqueous reacts with NaOH aqueous to give a salt and a water. Salt would be sodium methanoate. HCOONA would be sodium methanoate, and H2O liquid. Now we're given the volume of sodium hydroxide added to to neutralize 25 cm cube of methanoic acid, we can work out the concentration of methanoic acid. How? Always draw a table. To work out the unknown concentration of analyte in titration, always draw a table where you have the acid and base column, starting with the amount. We don't know yet, but we do know concentration for sodium hydroxide. What was that? 0.2. Volume, we know, would be 0.0225 dm cube. Let's just make sure that we have 0.2 mole per dm cube so that we can work out sodium hydroxide. Amount to be 0.0045. N equals CV. Therefore, concentration times volume for sodium hydroxide gives us 0.0045 mole, which equals to the amount of methanoic acid. Why? Because 1 mole of sodium hydroxide reacts with 1 mole of methanoic acid. The volume we have used for methanoic acid was 0.025 dm cube. Therefore, N equals CV. 0.0045 divided by 0.025 will give us the concentration, where the concentration would be 0.18. 0.18 mole per dm cube is our answer. There seem to be many ways to measure the rate of reaction for the particular reaction. Starting off with how gas is being produced suggests there will be volume of gas produced over time. Volume of gas using gas syringe produced over time. Easy to mark. However, there are other methods that we can easily guess, and that would include how there will be mass loss of carbon dioxide. Carbon dioxide being lost will lead to significant mass decrease. We could have mass change over time as well, where this is reduction in mass. We could also have decolorization, color change. And why is that? Bromine liquid is orangey brown, which which is lost by bromine becoming HBr, we would no longer have that orange brown color. So color change over time would also be indicative of the reaction rate. Another easy question. Catalyst increases the rate reaction. How? Lowers the activation energy. And how? How does catalyst lower activation energy? By providing alternate reaction pathway. Carboxylic acid reacts with alcohol to produce an ester, and also water, because this is a condensation reaction. In our case, methanoic acid reacts with ethanol. So we want to show how ethanol reacts with methanoic acid via condensation, where we're going to remove H2O. We're going to join the two. Draw the full structural formula of the organic product ester and state the name. Stating the name can be quite confusing, but remember how methanoic acid deprotonates to methanoate ion, so that we can refer to the left part of the molecule to be methanoate and the right part of the molecule to be an alkyl, ethyl. Therefore, the overall name of this molecule will be ethyl methanoate. Complete combustion of ethanol will have C2H5OH reacting with oxygen to give carbon dioxide and water. Liquid ethanol will react with gaseous oxygen to produce gaseous carbon dioxide and liquid water, unless we've got enough energy released to vaporize the water, liquid water, to gaseous water. 2 carbon dioxide will be produced and 3 water will be produced. From how many oxygens? Well, we have 7 oxygen atoms on the product side, therefore we will need 7 on the left reactant side as well, therefore 3 oxygen molecules will be consumed. Section 11 of the data booklet tells us what? Tells us the bond enthalpy values, meaning we will work out our delta H using the sum of bond enthalpies broken minus sum of bonds formed, bond enthalpies formed. How many bonds are broken? Firstly, we have C2H5OH. Within C2H5OH, let's draw C2H5OH. COH. We have carbon to carbon, that's 1. We have carbon to oxygen, that's again 1. Oxygen to hydrogen, 1. Carbon to hydrogen, 5. For oxygen, we have oxygen double bonded to another oxygen times 3. And the sum of these bond enthalpies will be bond broken. Some of the bonds formed would be, firstly, going to represent these in a different color. CO2, carbon double O, 4. 2 carbon dioxides means 4 carbon to oxygen double bonds. H2O, HO or OH, there's going to be 6 water molecules and therefore 3 water molecules and therefore 6 OH bonds. We can look these up in the data booklet, section 11, where bond enthalpy values are displayed. We'll work out carbon to carbon 3, 4, 6 and all for the rest of the other bond enthalpies. And if we do the math, we'll have 4731 kilojoules per mole, that is inputted. 4731 kilojoules of energy inputted and 5994 kilojoules of energy released. Overall, this will be a negative value, which meaning that we will have an exothermic combustion reaction, minus 1263 kilojoules per mole. Bromine reacts with but2ene as an electrophile, where but2ene with the double bond, electron-rich double bond, will electrophilically attack the bromine electrophile. We call this reaction electrophilic addition reaction. As a result of the electrophilic addition reaction, bromine will be integrated into but2ene, which loses the double bond. Therefore, we will have 2 bromines on carbon 2 and 3 each. But2ene can undergo polymerization. Where each repeating monomeric unit is a but2ene without the double bond, so that there can be 2 covalent single bonds that extends from the 2 central carbons. But we want to show a segment that comprises of 3 monomeric units, for which we're going to slightly modify the structure to be extended as follows.